All right, well, welcome everyone to episode 0. In this episode, hopefully we're going to get environment set up and learn a little bit about some of the basics of Elixir. So elixirlang.org is the home of Elixir on the web. It'll be your friend. It's a constant resource for me for lots of different reasons, but you come to elixirlang.org and you'll find this link up here at the top. Here's the home page. You click on Getting Started. You'll come to this page, and it has lots of information about installers, distributions, precompiled packages. I will tell you that I have used 2 of these methods on this machine that we're on today. I had to use Homebrew because when I used the method I used on the other one, which was precompiled packages, for some reason I was getting an Erlang error that I couldn't figure out, and Google wasn't helping. So I just went to Homebrew, which I already had on this machine. So in either case, hopefully either Homebrew or one of these other methods or the precompiled packages would work for you. And you'll know you've got the right environment set up when you can run IEX and you get this nice little prompt here. Whenever I'm doing development, and especially when I'm learning a new language, I end up doing a lot of interactive driven development. And the interactive prompt in Elixir is called IEX. So some of the most basic parts that we'll be using as we go through this process is the IO output. So the IO module and puts does, if you're a Ruby developer, it does exactly what you think it does. And one of the tricks of the Elixir language is that the equal operator that you typically think of as an assignment operator, is in fact a pattern matching operator. And if the patterns match, the variables on the left side of the equal sign will sort of catch the values on the right. So in this case, X just caught the value of world because X and world pattern match. So now we can go back to our IO statement, and we can, in a very similar way to how you would do in Ruby, substitute a variable into the string. So that's how we get output. I use this a lot for many obvious reasons, the most common being really hacky debugging. So that's number 1, and we talked a little bit about sort of the assignment operator there, which is number 2. So one of the first things I want to tackle is one of the big mind warps for me personally when it comes to functional programming. That is the fact that functional programs don't have loops. Because variables are immutable and you can't change their value, there's no loops with a variable like an I that would loop through the loop. You could probably actually mimic those things, but the point is, that's not the pattern, and I don't want to find myself writing Ruby in Elixir. I would like to write Elixir in Elixir, and the point here isn't so much to learn Elixir and get things done using a particular VM or interpreter, but to learn how that language approaches problems. So one of the things, while we're on the subject of assignment, you can reassign a value, and you can do some of the things that you commonly would do with variables. So that's some basic stuff that we'll be using here in a second. So the best example, the simplest example I could think of to show how to accomplish what you would use a loop for in other languages is writing a program that will sum all the numbers from a particular number down to and including 0. So the answer for the number 3 would be 3 plus 2 plus 1 plus 0, which of course would be 6. So in a normal procedural programming language, I shouldn't say normal, procedural programming language, you would probably define a loop to count up from 0 to 6 or from 1 to whatever the variable you pass in is. You'd create an accumulator, each pass through the loop. You take the value of the looping variable and add it to the accumulator. At the end, the accumulator equals the value that you're looking for. We don't have loops in a functional programming language, so we have to come up with a different solution. So what we're going to do in this case is we're going to write a little program to do it. This is a little easier to do through defining a module than it is through interactive. Typically, a Elixir program, if it's just a module meant to be included in other programs, you would typically give the extension EX. If it's a script that you mean to have sort of main-like functions, you typically would give it an EXS extension, which is what we're doing here. So that's what we'll do. The first thing to know is that in Elixir, everything happens in a module. So we'll define the module example. And down here, we will go ahead and call a method or a function we'll define here in a second. And we will pass it the number 6 and hope eventually it will pass us out the result of 21. So to do that, we need to define a function, and it will be passed in a variable. And after you define things, you have to add the keyword do. I often forget it. You'll get sick of seeing me do this. I get sick of doing it. So in this case, we could do this in a pretty procedural way. Again, this is what we don't want to do. This is writing Ruby in, this is mostly writing Ruby in Elixir. And so the first branch of the conditional, if we get called with the value 0, simply return 0. Otherwise, return the value of this number plus calling the same function with the next smaller number. So whereas in a procedural language, you tend to think of loops as counting forward from 1, say, up to 6 in this case. In a functional programming language, you typically would count down from 6 toward some end state. In this case, we've defined it as 0. We could just as easily have defined it being 1 and say if limit equal 1, do return 1. So the way Elixir mimics loops, like most functional programming languages, is using what they call tail recursion. So the very last expression in the function is calling the same function with a slightly different parameter list. And the interpreter, the compiler, is optimized for that. And when this code runs, even if you nest it very deeply, you won't get into problems with running out of memory or blowing out the stack because the call stack got too deep. That won't happen. And this is basically how we would implement a program that would sum all the numbers from 6 down to 1. So you can see in the case where we pass in the number 6, 6 isn't equal to 0, so we pass to the else statement. And the call to sum with the value of 6 will evaluate to 6 plus the result of calling sum with the value of 5. And you can imagine the 5 will equal, when you call it with 5, you'll flip into the else statement, and it will result in 5 plus the result of calling sum with 4. And eventually you'll get to 0, and then eventually 0 plus 1 is 1, and that method will return 1. 2 plus 1 is 3, and then when you call it with 2, it will return 3. 3 plus 3 is 6, so when you call it with 3, it will return 6, and so on up until eventually it spits out hopefully the right answer of 21. And the way you run this is simply by calling Elixir and passing in the file name. And you can see, that I need a space between the minus and the 1. Let's try this again. And there we are, 21, right answer. But as I said, this is not a very Elixir-y way to solve this problem. And in fact, there's a couple ways we can make it slightly more Elixir-y, but we're going to hop to possibly the most Elixir-y, and we're going to talk a little bit about pattern matching. So just as I said, the equals operator is really more like pattern matching. When Elixir is evaluating what function to call, it also uses pattern matching. And the pattern matching and the function definitions is evaluated from top to bottom, and this is because Elixir is compiled into the Erlang VM, and that's the way Erlang does it. I imagine that's the way lots of functional programming languages do it. But in this case, when we call sum with the number 6, in this case, you can see the pattern matching here. We didn't call it with a 0, so this one won't match. So it goes into this one, and the result will be do plus calling sum with 5. Just like before, except now we're doing it across 2 different function definitions. And in this case, both these functions have the same arity, as we would say, meaning they have one parameter. But because of the pattern with this one is more specific, you can see that we actually have 2 different behaviors going on, even though they have the same number of parameters. And if we pop out of this with some luck, there we go. We're still getting 21. So this is the start of a couple interesting features of Elixir, both of which we'll leverage heavily in the coming episodes. One being the tail recursion here with sum calling itself with a slightly different parameter, and the other being pattern matching, and specifically pattern matching from top to bottom. So we just barely started to scratch the surface, but I'm trying to keep episodes short, so we will continue this next episode. Well, I wanted to make a quick addendum to this this video because I made a mistake, and it seems like a pretty honest mistake to me, and it might be a mistake you make as well. And certainly I said something was wrong, I want to set it straight. So when I was talking about tail recursion, it matters very much, not just that the function call in question is the last, sort of in the last line of the function, but it matters how the function is evaluated. And I'll show you what I mean. So here I've got basically the same functionality implemented two different ways. The two method signatures for method one the two function signatures for method one are the way I was doing it before. Method two we'll look at in a minute. So method one, you can see that the call to method one with limit -1 is the very last thing in the function call, but the point is it's actually not the last thing evaluated. When the interpreter gets to here, it has to hold this memory frame for a minute, hold the value of limit, go and get the results of method one, and then after that returns, then it adds limit. So in doing that, method one is no longer the last thing evaluated in the function, and so the function doesn't get the kind of optimization we'd like to see from tail recursion. And you can see that, so here I have method one and method two. Well, before we do that, we'll discuss method two. So method two, these three signatures basically are passing an accumulator around through each pass through the function, and that's actually what is going to end up holding the total value of the addition. So you can see the normal case here. So in the first case, when we just call method two without an accumulator, we just call method two with an accumulator and start it with 0. The method two function here takes that accumulator, adds to it the current value of limit, and then calls itself with limit -1. So in this case, not only is the call to method two the last thing in the function, but it's also the last thing evaluated in the function. So this will get the tail call recursion optimization that is a feature of the Erlang VM. And then of course we still need our terminal case, which in this case is when the limit is 0. And instead of returning 0 as we were before, we simply return the accumulator and we're done. So just to prove that the method, or the two different methods are functionally equivalent, I'm calling each of them with the same value of 1,000, and we will see that they both print out the same answer. However, we'll see that when we start calling these with much bigger values, there is a difference. We'll do these one at a time. So I'm not even sure how big this number is. Let's see. Looks like we're calling it with 100 million. And we will see, and I will pop my, well, hold on, we'll do this, and then we'll come over here, and you can see that the beam, which is the Erlang VM, is starting to take up more and more memory. You can see I'm up to 4 gig of memory now, and you can obviously see that the function is taking quite a bit of time to do what it does. So we will let it finish. And there we got the answer, presumably the right answer. So we'll hop back in here, and now we will not do method one, we'll use method two, and just to make a point, also calling method two with 100 million, and we'll pop over here, and you can see the beam doesn't even have time to pop up in the task list. It's taking up a lot of memory. Obviously ran much quicker, and we still get the right answer. So when you're planning for tail call optimization, you've got to be careful that not only is the function call the last thing in the function, but it's actually going to be the last thing that's evaluated. So there's a quick update.